Hello, everybody. Welcome to CS 202, the Mexico edition. Can you all hear me well? I hope so. Things seemed to be somewhat okay on the first class that I did today, but it was a little bit. There was a little bit of a delay uh, on the stream, so I wouldn't be surprised if that happens again. In fact, from what I'm looking at here, there's a couple of seconds delay. I am going to try to just keep as little open as possible to avoid issues. But yeah. Okay. Well, hope someone's at least here. You're all very quiet today. Regardless, today we're going to learn a very important topic. So if you've been keeping up with the lectures, which I hope you have, you will recall that I did say on the last lecture that we are done with C++. Like we have finished all the coding or programming like syntax that you're going to learn. And from now on, it's all about concepts and applying the knowledge that you know. And thank you. I just got here though, so I've been mostly just home. Uh, I got here on Saturday, so yesterday I was just setting everything up, and now I'm teaching. So, but it's still nice. Is it just you or just laggy? It might be a little laggy. I am recording locally, so maybe that's causing some delay. I mean, let me open up the stream for a second and see if there is a delay on my end. Let's see. Oh, I do see that with the webcam. It is a little laggy. Hmm. You know, the only change that I did between like this stream and the one before for the previous class is that I started recording locally because I forgot to record locally last time. So that might be pushing the laptop a little bit too much. But is the audio okay? Because that's kind of the important part. If my video is laggy, it's not too bad. What's important is that the actual audio is not choppy, because that would be bad. I could stop recording locally, but I'd rather record locally because if anything, that'll be cleaner if there is some disconnect or something. I have better internet here than I have at home, so it's not the internet per se. I'll tweak with the settings though. But okay. All right. So let us begin. Today, we're going to be looking at a very, very, very important concept known as recursion. And it is very important because it is very important. And it is very important because it's very important. And it's very important because it's very important. And on and on and on. Because that's what recursion is all about. Repetition, repetition, and repetition. But not the kind of repetition that you would do on the loop. But in this case, it's going to be with functions. Uh, so, what is recursion? Recursion, and some people will say recursion is recursion, but that's kind of what it said other. What recursion is going to be a concept of trying to solve a problem by reducing it into a smaller version of itself. So basically, when you have, oh, and to answer your question, yes, you can. If you would like to do both, then I will let you do it. The main goal of the coding one is as an alternative if your phone is not compatible. But if you would like to do them both and you can, then you're more than welcome to. Okay, so recursion. The process of solving a problem by reducing it to a smaller version of itself. That doesn't say much as to what recursion is, but it turns out that explaining recursion is like, if you ever watched the first Matrix movie, uh, when Morpheus tells Neo like what the Matrix is, he's just like, the Matrix is not something that can be explained, it's something that you must see yourself kind of thing. That's kind of what recursion is. It's really hard to explain it without you just doing it. And even when you're doing it, it's still one of those concepts that you're just kind of have to sort of get used to. A lot of people are usually very uh, adamant about using recursion in their problems, but the whole point is that recursion is there to make your life easier, not harder. You know what I'll do next time? I just noticed is I'm using Wi-Fi when I can actually use Ethernet. That'll probably fix the stream for next time. I forgot about that, so bear with me on that. Even though I'm talking about something like back of my mind, it's like, yeah, but that's what's messing it up. Okay, so yeah, because like I said, the connection's pretty good. So yeah, I don't know if I just, yeah, I don't want to try just trying to plug it in right now and like the whole thing breaks down, but I'll do that for next one. Okay, Wi-Fi is not good, even though I'm literally next to the router. But okay, so like I said, I just have to show you recursion for you to understand it. And so let's just start by writing a recursive function that does something. Okay, so let's go ahead and write a function that is going to print the number 1 repeatedly, like an infinite loop. We know how to do that with loops. We know that we can just go ahead and say something like while true or while 1, just infinite loop. I could go in there and say cout 1. And this will literally spam to the terminal 1 for infinity or until you terminate the program, right? This piece of code you learned in 135, you know how to do. You could be blindfolded and code it probably. Okay, there is another way you can do that without using loops. So yes, whenever you're thinking about repetition, it will be uploaded, yes. Whenever you're thinking about repetition, you're thinking about using loops. Well, I'm here to tell you that there is another way, and that's going to be through recursion. Let's go ahead and write a function. I'm going to call this function foo, but you can call it whatever you want. And by the way, try a different browser because most people didn't have issues last time, which was like an hour ago. So literally, I have 15 minutes between streams, and they weren't having this many issues with the stream. But yeah, so I got a function foo here, and I'm going to make this function do the exact same thing as the other one, which is print, technically, in theory, for infinity, though there's some catches here, the same thing. So what am I going to do? Well, I'm going to take my same cout statement, and I'm going to put it in the function. And you're like, well, hold on a second. This function is only going to print it out once. You got to call it with another loop or something if you want it to print more than once. You are correct in its current state. But what am I going to do? I'm going to put one more line of code in this function that's going to do this whole process. And it's a function call to a function. And not just any function, but the same function that I'm at. This is like function inception, or what it's properly known as recursion. In this case, let's understand what's going to happen in this code. Somewhere in my main, I have to call it, yes. So I have to write something like foo in main or somewhere in my code. When you finally get to that piece of code, though, if you're looking at this with a debugger, with a little dot, where the line is, it's going to enter the function. It's going to print out the cout1. Then it's going to see the function call. What's it going to do with the function call? Well, it's going to create a brand new function, a new instance of foo, and then it's going to run it. So what's it going to run? The cout1, so we're going to get a second one printed, and it's going to see the function call again. What's it going to do then? Exact same thing. It's going to create another instance and print out another one. So for every time that this function gets created and ran, it's going to print out one of these. And in theory, you have achieved the exact same output, which is just infinite ones. Basically, there's going to be infinite versions of foo in there, and each of this is going to contribute a 1 to the terminal. Just like the while loop, though, there is no way to stop this madness once you make it run. It's going to run forever. However, unlike the while loop, though, this will not run forever, at least in the terminal. Whereas the while loop, it uses very little memory. Sure, your terminal is going to get overflow with ones, but it's probably not going to crash. It's just going to print ones forever. Might get laggy or something, but it'll print them for a long, long time. In this case, though, every time that we're making a function foo, it's it's allocating memory. Now, the function foo here is very lean. There's no arguments or parameters that are being part of the function. There's no local variables. So there's not a lot of overhead associated with this function call. But it still takes a little bit of memory because whenever you have a function call, there's context switching that's happening behind the scenes. The code has to remember where it came from, what the next line of code is. So like when you finish a function, we take this for granted, but it needs to be like, oh, okay, I finished the function. Where did I come from? Like, who called me? What's the next line of code that I got to run? So that information in behind the scenes, the operating system has to keep track of that. And so, you learn about this when you take CS326, but this information is kept in something known as a call stack. And every time that there's a function call, you got your main, which is a function too. And then on top of that, if you call a function, you'll see here like function foo, and then that calls another foo. And in here is going to be an address, and that address is going to be the memory of the, sorry, it's going to be the address of who called you, like the last line of code that you ran from the previous context. So it'll be like little arrows. In fact, you'll be drawing a bunch of arrows in 326 like that. Like, okay, so that way it knows what the next line of code is to run after the function terminates. Okay? So it's very important that it does that because otherwise the code will get confused. It'd be like, I'm running a function and then be like, what's next? Like, who called me? Like, you might be like, oh, we'll just look for the foo function call in main. Okay, sure, that works if there's like one foo function call, but what if there's like 5 of them? Like, you might be using the AVS function, absolute value function in C++. You could be using it 5 times in your code. How does it know which of those it came from? So it has to keep that kind of information. And because of that, every time you do a function call, in addition to keeping local variables and arguments and references, if it's a class function, it keeps the this pointer, all that overhead that it keeps, static variables if there is, that takes space. So even in this super lean version of this function that there's very little involved, there's still a little memory that it takes every time you do this. So by the time you print about 100 of these ones, that starts to build up. And in theory, you're going to get to the point where you're going to run out of memory. Well, it's not very much theory because you can actually get that to happen pretty quickly with recursion. In fact, if I run this piece of code right now, I can guarantee you that it's going to take probably less than a second before it's going to crash. But it's not going to be any kind of crash. It's going to be as what is known as, surprise, surprise, Stack Overflow, like the website you all have been on at some point probably. So you might be asking yourself, okay, why do I want to use this method for like repetition when loops don't have any of these problems? Loops don't take extra memory. There's no context switching involved, which takes time too, by the way. It's not immediate. It does take some overhead time as well. This does not require that. Sure, there's still a little bit of information. If when you take 218 assembly, which would probably be the next class, the assembly code for this, there's a jump statement here that basically checks, like whether the loop should iterate or not, and then decides to go there. So there's still a little bit of code involved, but that code is not like going to grow based on the amount of times this iterates. It's a static amount of code. This stuff though has a lot of overhead. So you again might be asking like, why do we want to do this? It's inefficient. It's uh, it's hard to conceptualize a lot of times. So why? And the answer is because some of the algorithms that you're going to learn in your CS career, particularly in CS 302, which is the data structure class, but also analysis of algorithms, those algorithms are not so easy to program using loops. A lot of them require this concept of like reduction of a problem into smaller pieces and just sort of are intuitively recursion. Okay? So like if I tell you, okay, can you please like give me all of the contents of a list? Start by the first one and then take the next of the first of the remaining set. You could code that with iterative code, but you could also code that with recursion, and it might be more intuitive to code it with recursion. And that's what it turns out to be. When you get to 302 and you're learning something like quicksort, it is way easier to program it using the concept of recursion than it is to code the iterative version, which is known as lamp sort. You can check these out if you're curious, and at the end of the day, it's good to kind of learn about this stuff before you take the class if you want to make the class more enjoyable. You're not like trying to pick all these things at once, but quicksort and lamp sort are really great sorting algorithms. But this one's like heavily dependent on your using recursion. And this is basically just the iterative version of that. When you look at the source code of these, and you are going to have to code quicksort in 302, uh, but when you look at LambSort, which you probably won't code in 302, depending on who you take it with, you will see that the code for LambSort is just way more complicated. Like you just look at it and it's harder to follow. And that's just because it happens that like it's just like that. I mean, some code is just easier to explain with recursion. When you're doing traversals in trees, which is something we just did in 302 a week or two ago, coding a traversal with recursion is like 3 lines of code. Trying to do the same thing with iterative code would require like using some sort of stack and overhead. It just it's unnecessarily long. And at the end of the day, as programmers, you want to write the least amount of code to do the most amount of work. So that's why recursion is so big. And initially, you might be hesitant to appreciate it, but it's one of those like necessities. It's a necessary evil per se. When you're trying to optimize something, recursion is not the way. But when you're trying to prototype, recursion is very much the way. So if anything, you code something recursively, you make sure it works really well, and then if you want to optimize it, then you start thinking about making it iterative and all the nastiness that you may have to do that. But that does bring up another point. When you have iterative code, you can convert that iterative code into recursive code one way or another. I don't think that there's any code that would be iterative that cannot be turned into recursion. With the one catch, of course, being that doing enough repetition is going to suck fault because you're going to run out of memory. Now, internally, this is not something that's part of this class, but maybe 219 you hear about it. Internally, there are some limitations on how many of these function calls you can stack on top of each other before the program terminates. So you're not particularly running out of memory completely when you get these Stack Overflow errors, but and there are ways to tweak it so that you can use more memory, but you definitely need administrative rights to do that kind of thing. So you're not going to be able to do that on salary. So just be aware of that, and just be aware that you know recursion can be used, but it's still you're still going to be very limited because like most of the time in the real world, when you're coding something, you're going to pass a lot of data through it, and that's when recursion it stops being useful because of the overhead associated with it. Okay, so after discouraging you about recursion, you're trying to teach it to you, but I'm telling you, this will make more sense to you when you take 302 as to why it's useful. Okay. For now, these are all going to be toy examples, and you're going to kind of shrug and be like, I could just do this iteratively 10 times easier. But just trust me that, you'll get there someday. And then you'll be like, oh, okay, now I know why I learned this. Or, damn, I should have learned it because now I really need it and I can't wrap my head around it. And so it's traditional that when you're learning recursion, one of the first things that you should do is talk about the Fibonacci sequence. So let's go ahead and show you that. And my chair just like sank down. Uh, it's one of the things you're gonna notice is that all right, I'll just leave it down. Is that with recursion, you're just gonna have to kind of take it on a case by case basis, and there's no like, okay, step one, step two. This is not like templates where like, okay, this is the syntax. This is what you're gonna do exactly to convert this into recursion or vice versa. It doesn't really work like that. This is on a case by case basis, and you're just gonna have to understand it. Uh, but I'll do my best to try to give you some pointers as to how to convert things. Okay. And I still got to talk to you about base case, recursive case, but we'll get there. Let's just talk about the Fibonacci for a minute here, okay? So what is the Fibonacci sequence? The Fibonacci sequence, you probably learned that in your math class at some point, or hopefully have learned it. But if not, you can Google it and figure out pretty quickly. It's just a sequence of numbers, and there's a rule to generate these numbers, as there are for any sequence. And the rules are that you're going to take the previous two numbers of the sequence and you're going to add them together to get the next number in the sequence. So depending on who you ask, Fibonacci sequence will start with 0 or at 1, but you still need to have the first two numbers of the sequence defined. If you don't have those, then the sequence doesn't work. So once you have this defined, then the rest of the numbers in the sequence, again, are just an addition of the two. So in this case, the next number of the sequence is actually going to be a 2. How did I get that? Well, I added the previous two numbers, which are just 1 and 1. 1 and 1 is 2. What about the next one? All right. Well, 1 plus 2 is 3, so that means that the next number in the sequence is a 3. What about after that? Well, a 5, 8, 13. What about the next one? Well, you got to take the previous two numbers, so that's the 8 and the 13, add them together, get the result. That's the next number in the sequence. What about after that? Add those two together, get a 24 out of that, or not 24, sorry, 34, and there's the next number, and so on. So that's your sequence. So now, if I went and told you, okay, how do I write some code that will generate the sequence for this? Like, can I write a program that can generate this code? Well, before you could probably do that. What would you do is you just hard code the first two numbers and then put it in a for loop, depending on which number of the sequence you want. So if you want the 5th, the 6th, the 100th sequence, you put it in a for loop, and then you just basically compute the next number by taking the previous two, add them together, and so on. So to save some time, I went ahead and have that code already to go. So I'm just going to share it with you because, again, we're not really interested about iterative code today. We're interested about recursive code. So I believe this should be good to go. So in this case, we have a function because I thought, why not make it a function? We're going to call this fib for Fibonacci. And we're passing in an argument n, which is going to represent the end number, I suppose, in the sequence. And so, again, in my case, I'm going to say that the first two are 0 and 1. And this is going to print out all the numbers in the sequence. That's why you see the cout statement there. You will notice that I'm not printing out the 1. That's just the way I set up the code. I think I don't need to print out the 1. It'll be printed on the first iteration. Yeah, and if not, you could just cout 0, 1 there or something. Actually, no, I do think I have it. See, there's a 1 in there. So yeah, okay, so I do have it there. All right, so, when you do this, what's going to happen every time you loop is you're just going to take to figure out the next value, you take the previous two numbers, which I preset to be 0 and 1, and then compute that and just print it out. So, 0 plus 1 is 1, and then update the two sort of numbers so that you can add the next one, right? So in this case, this is the second previous and this is the current previous. So what you do is you take the current previous and set the second previous to that, and then take what is the new number and set that to the previous, run it again, rinse and repeat, and this is how you compute it iteratively. This is efficient, fast, and good. Okay. However, how would you do this recursively? And would it be more intuitive to be done recursively? For that, we turn to our people in the math department. If you ask somebody in the math department what the Fibonacci sequence is, they're just going to come out and, they always pull out their fancy symbols, and they're going to give you something like this. And they're going to say, well, the Fibonacci sequence is defined with the following function. We got f of n is equal to f of n minus 1 plus f of n minus 2, where f of n is basically going to be the nth number of the sequence. We also have two base scenarios, which are known as the base cases of f of 1 and f of 0, which are 1 and 0 respectively. Or, they could also say 1 and 1. Again, some people say Fibonacci starts with 1, not with 0. Doesn't matter for our purposes, right? So you see a formula like that. You might also see it in this representation like this. You'll see f of n is equal to, and then you see f of n minus 1 plus f of n minus 2, where n is greater than 1. And then you have your two cases where n is equal to 1 and n is equal to 0, right? So this is what you would see on a math book. And a lot of the times when you're trying to take, code that you have a problem that you have basically analyzed and converted into a mathematical equation, and now you want to code that equation, you have these kind of problems. Well, when you're looking at something like this, it's not particularly loop friendly. If you just see something like this, in fact, it's just because I explained to you how this works, but unless you're like good at math, this might look a little bit alien to you. Well, it turns out that when you write the recursive version of this code, this right here is almost exactly how the code would look like with recursion. And that's the power of it. That converting, understanding this Fibonacci sequence as a mathematical problem is actually understanding the recursion behind it and coding it. So let's go ahead and try to code the Fibonacci sequence as a recursive function. Before that though, let's talk about the f of 1 and f of 0 and what those mean and why we need them. Why do we need f of 1 and f of 0? Well, this mathematical formula here, that the f of n blah blah blah, there's a lot of variables in there, and you can't really figure out what the real numbers are unless you plug in something for this n, right? So you need a starting point. Those starting points are this f of 1 and f of 0, right? Because if I tell you, like, add all these numbers together, but I don't give you any numbers, you're like, what do I add? And so here it's saying, start with these numbers and then plug them in so you can figure out what f of 2 is equal to. So like if I want to compute what f of 2 is equal to in this formula, what I do is I plug in, n is equal to 2, right? So let's do that very fast. So if I want to solve this, I say, what is n is equal to 2? Well, then f of 2 is equal to f of n minus 1, so that's 2 minus 1. So let me write the parentheses smaller. Plus f of 2 minus 2. So what is 2 minus 1 equal to? Well, 2 minus 1 is equal to 1. I hope you guys figure that out. And that's 0, right? But you still got things in terms of f. Except that's where these base cases come. We know what f of 1 is equal to and what f of 0 is equal to, right? So then we can do the substitution and plug those in. And now this is just 1 plus 0, which is 1. So then f of 2 is equal to 1. What do we want to compute f of 3 now? Well, f of 3 using the same formula, we got to take 3 minus 1 plus 3 minus 2. That is equal to f of 2 plus f of 1, right? However, if we had just started without computing f of 2, we know that f of 1 is equal to 1 because that was given to us. But we don't know what f of 2 is equal to, right? We don't know what that is. Obviously, we just computed it, so now we know. But the point is that if we didn't, we would have to figure that out ourselves. Now we know that it's equal to 1, so we can just substitute it in. That tells us f of 3 is equal to 2, right? So you can compute this because you have those base cases. But if you didn't have this, you couldn't compute anything. In fact, if I go in and tell you, okay, cool, what is f of 10 equal to? Well, f of 10 is equal to f of n minus, we said n minus 2 or n minus 1, right? N minus 1 and n minus 2, so that's f of 9 plus f of 8. But I don't have any of those, so I had to compute those manually too and figure that out, right? So from the mathematical perspective, The only way that you can compute these is if you start a starting point. All right? So those are base cases. So when you're writing your recursive function, you always want to have these base cases as well. What the base cases are going to do is they're going to make the recursion stop. Obviously, I said recursion, you can run it infinitely, but in practice you can't because you run out of memory. So if we're actually trying to use recursion in a practical point of view, so actually code recursion, which you are going to be doing, then we need to tame the monster or something, right? So in this case, we do that with the base case. The base case is going to be how to stop the recursion. What would be sort of the equivalent to a base case with loops? That would be the statement on your loop, right? So when I say while something and run this code, we know that whatever that statement or expression in here is, technically it's an expression more than a statement, I believe. You gotta remember my compilers, but whatever is in there is what stops the loop, right? Whenever some condition is met, this loop terminates based on what's in there. That is the same thing with recursion that your base case achieves. It's that stop, which you want to make something practical that can stop before you run out of memory. So that's one component of the recursion. The other component of the recursion is going to be what's known as the recursive case. With a loop, the fact that you write the word while, it means that whatever is in between these two curly braces is going to keep repeating until the stuff in the blue makes it stop. So the while loops don't require any sort of extra writing to basically tell it that it's got to keep going. With a function, that's not the case. With a function, you still got your little curly braces and you got your function name, but when your function finishes, it's done forever. The way you make the function keep going over and over again is by making a function call to the same function, right? That's what achieves that recursion, that you have that foo that keeps getting called over and over again. That's known as your recursive case. You don't want to run that line when you actually meet your base case, right? So whenever you want the recursion to stop, you want that line not to run. So what's the easiest way to do that? Well, there's a lot of ways, but the easiest thing I can think of is just put it on an if statement. So whatever you would put inside of the if statement is what you would put in your while loop, right? So to summarize, the major components of a recursive function, you can think about that as three major components. But really it's two and something. But that something is kind of important. So you need to have at least one of each of these things, okay? The first thing I would say most important, just because of how recursion is, you know, hardcore, is you want to have a base case. So the first thing you got to think about when you're doing recursion maybe is how to stop it, frankly. When you're writing a while loop, you typically write you know, the stuff in the blue first, right? Because you're writing while and then you put some expression there. So you kind of do loops that way too, right? Like you already have in your mind how is the loop going to stop before you even write the concept of the loop. But nothing stops you from writing code like this. Just write the word while, leave whatever's in the parentheses blank, and then just write your loop and then go back and finish in your while. You could do that too. There's no crime against that. So that would be the same thing as saying, okay, let's not do the base case until later. And I've seen people do that, and it's okay. So if you're comfortable doing it that way, sure. But remember to then come back and actually do your base case. Okay? So again, I want you to think of the base case as when the recursion stops. Like what is the condition that must be met for the recursion to stop? The next component that you should have in your recursion is going to be the recursion itself, right? If you're doing this recursively, it means you want it to repeat until the base case is hit. So that's typically just going to be a function call, just a function call to the same function. So basically calling yourself, and by that I'm saying calling the same function that you're at. So if you're in foo, call foo again. you got your basically your recursive definition is another name I've heard. Now we are going to get a little more advanced into this recursion thing, but you might have some parameters that you are going to pass in that function call. So the function call might not be exactly the same, but you want to have some information passed between, because one thing you're going to notice is that in a loop, you can access variables outside the loop to be able to update things, right? So like if you got, you got a while loop and you want this to run 10 times, you can put a counter outside, start this at 0, and then like your base case could be, count greater than 10, and then you just, do count plus plus. You can do a lot of things in here. With a function, in theory, you could do the same thing. I mean, you could write a global variable and use it as a count, or you could use a static variable inside the function, which is slightly better than a global, but still, I would say not the right way to do recursion. The best way to communicate information between each call of the recursion is to send data through the parameters of the function. That's going to make your recursion be more sane and easier to work with. Otherwise, it just becomes a mess and it's highly discouraged. So, the function call might be slightly different if so that you know how to stop it. Because, I mean, at the end of the day, your base case, something has to happen to stop it. And if the code is the exact same every single time you run it, you're never going to hit that base case. So those parameters are going to help you hit that. But in the case of object-oriented programming, you could, in theory, make it a class variable. And that's the one that keeps getting modified instead of actually a variable within the recursion. When we get to linked list, you get to see a little bit more of that. Finally, we have that third thing that I'm always hesitant to put, but I would argue that it is important, and that is to basically do something. To get us closer to our goal. Which is, I would say, what's the word I'm looking for? It's a subliminal message. No, no, that's the word. No, what's the right word? Basically, it's code. Yeah, it's code for getting us closer to the base case, right? What you're doing should, in this pass of your function, I'm hesitant to say iteration because we're no longer using loops, but what you're doing in this instance of the function or pass should actually be something that's getting you closer to what you're trying to achieve, such as printing a bunch of ones, could be as simple as that. But because you have a recursive case, you should also be doing something that is hopefully getting you closer to that. So like if your recursive case is a count, you want to print something 10 times, that might be as simple as increasing count plus plus, but also doing something else. So yeah, do something to get you closer to your base case so that you're not here all night just going in circles. Okay? So now that we understand the core basics of recursion, let's go back to our Fibonacci dilemma. We have this, and we need to functionize it, I suppose. Make it into real code. Take the math and make it into actual practical code. Well, it turns out this is going to be easier than you think. We have this. We know what our base cases are. So what do? Well, let's go ahead and write a function. Now, this is the value returning function in math because f of n is equal to something. So it makes sense to make it a value returning function in code. So we're going to write it int. I mean, I could make it a long because make bigger numbers, but I'll stick with int. You know, I would want to call this fib, but let's go with f just so that it matches what the mathematician said. And there's some n, so we're just going to make that some parameter. Why not? All right. So what do we put in the function? Well, we know how to compute the next number. All we got to do is just take that f of n and return that, right? So we can say like return And we know that to compute this number, it's related to the previous two numbers as shown here. So let's literally write f of n minus 1. We'll do that computation there. I mean, you could do it outside, but why not do it there? Nothing stops us from, like, if I have a function call and I have some parameters in there, I can do math directly on the function call. Just be careful with things like post increment and, you know, post decrement or pre increment and post increment, where like things might happen after the function call. So, you definitely don't want to change this code into this, because then you'll be here all night, right? Because the end is not going to get the updated value. It's going to get the current value. So, be careful about that, just like you would be with any code. You could do that though. That's okay. But I'm gonna, I don't want to pull any weird concepts. I'm gonna keep it as simple by putting n minus 1 there, plus f n minus 2. Okay, that's easy. However, I I kind of combined my recursive case and my do something together, but I don't have my base case in this function. This is going to, if I call this with like f of 5, it's going to call a bunch of recursions. It's going to go into negative numbers, into like negative infinity, or crash at some point before it gets to negative infinity. So I still need my base case in here. I need my way to stop the madness of the recursion. And I definitely want to do that before this line of code, because if I do it, if I have my recursive case before my base case, then the base case will never be seen. It's like